Alright, this video is just going to have quite a few examples of working with linear models. So let's jump right in. Number one, leasing a particular car costs $850 plus a monthly fee, a monthly reoccurring fee of $225. Create a model that gives the total cost for a given number of months leased. Alright, so first we're going to talk about X and Y, independent, dependent variables. And think about it, you've got a monthly fee of $225. So depending on how many months, that's going to change what you pay, right? So because it depends on how many months, my X value is the number of months. And remember, the independent variable is generally some kind of time. So number of months is the independent variable. Now, depending on the number of months, we're talking about leasing a car which has a total cost. So Y is the total cost of leasing this vehicle. So in talking about units of measure, for total cost, we're talking about money, and for the independent variable, we're talking about months. Again, a time reference. All right, let's jump in. What's the Y-intercept? Well, before you even start making these monthly payments, you have an initial cost of $850. So that's where you start. You're at the car dealership, you give them $850, you sign the paperwork, and now you've got a car. So the slope is the 225. Well, let's use my symbols here. So the slope is 225 because every month you're paying 225, and this is increasing because you're paying it, right? Your cost is going up every month. Let's put those together to write our formula. Y equals my slope times X, X is the number of months, plus the Y-intercept. And that, our linear model, we can use to estimate all kinds of things. So what would it cost to lease the car for 6 months? Well, 225 times 6 plus 850. We do the multiplication first. So Y equals 1350 plus 850. It's going to cost $2,200 to lease the car for 6 months. There you go. Let's say you have a budget of $3,800 and you want to see how long you can lease this car. Well, we got to work backwards. We've got the 225x plus 850. Well, $3,800 is the total, so it goes with the Y, the total cost. You're trying to figure out how many months, which is X. So I've got to solve this. First, I get rid of the constant. I subtract 850 from each side. So 2950 gives me 225x. I divide both sides by 225, and x is 13.1. Now, can you do something for a partial? You can't lease a car for a partial month, right? Go ahead and try. Well, I shouldn't say that. I've never leased a car. I don't think it works. So we would have to just say, I can pay for 13 full months, so that's what it is. I don't think they do partial months, but I could be wrong. Let's go to a new problem. A cell phone plan charges a flat rate of $20, flat rate, plus 50 cents for each kilobyte. So hopefully you kind of think flat rate, that's one time. For each, that's reoccurring, right? Because every time you use a kilobyte, you have an additional charge. So we can create a linear model. Well, I know it starts with Y equals, your slope is a reoccurring, it happens all the time, and therefore my 50 cents per kilobyte. So X represents the numbers of kilobytes, plus your one-time flat rate of $20. Y represents your total cost. Okay, and this is actually an example where our X value is not time, because kilobytes aren't time, they're data usage. So that's why I said almost always, but not necessarily always. All right, so Y equals 0.50x plus 20. How much will a bill be with a 350 kilobyte of data usage in a given month? Well, if I have Y equals 0.5x plus 20, and X is the number of kilobytes, then 350 I plug in there. So 0.5 times 350 plus 20. I do the multiplication first, so Y equals 175 plus 20. Your bill would be roughly $195. Yeah, that's a lot. And letter C, how many kilobytes of data were used if the bill was $32? Well, again, we have our formula. 32 is the total cost, so it goes in for the total. and I solve. So my first step would be to get rid of the constant. I subtract 20. Those go away. 12 equals 0.5x. Divide both sides by 0.5. X is 24 kilobytes. So for this particular example, if you only have a $32 bill, you only use 32 kilobytes of data. All right, let's get into a little bit bigger of a problem. We've got a survey that shows percentage of smokers in the U.S. from 45 to 2012. And it says, have you yourself smoked any cigarettes in the past week? So we want to find the linear model, which represents the citizens who smoke. I don't know why this is a question mark. It should not be a question mark. That's our goal for this problem. And we're going to go through some different steps to do that. Notice it says from 78 to 2012. That's this section. We don't really care about these people over here, right? Nothing good happened before 1978 anyway, right? Wink, wink. I wasn't alive then. Whatever. Okay, so first, what is y value, the dependent variable, and what's the unit of measure of y? Well, if we go back to our picture, here's y. What does this represent? Well, it's the percent who said yes. So it's the percent who smoked. Because if they said yes, then they smoked. So the unit of measure is the percent. So the percent who smoked is the dependent. What's the independent variable? Years. Right? The years across the bottom. Yeah, come on, here we go. All right, so let 1978 be the starting point. When it says that, it means let's draw a new y-intercept, a new axis right through 1978. So we're saying that this has an x value of 0. So 1978 means x is 0. That means the y-intercept would be 38, because that's where it crosses the graph. Now, I want to just go one more second with this. If 1978 is 0, 1981 is 3 years later, so that would be 3. Then 3 years later would be 6, 9, 12, right? Those would be the values of x. So notice that 1978 does not have an x value of 1978. It has an x value of 0, and all the years after that will be, representative of that. All right, so let's find the slope. So we know that we have a point 038 because that's our y-intercept. And then they give us a point here, which is in 2011, with the point of 22. Okay, so now let's think about this. In 1978, x was 0. 2011, x will be, well, how many years later is that? 1978 to 2011 is 33 years. So my x value will be 33, because it's how many years later it is. Hope that makes sense. Okay, so now let's do our formula. y2 minus y1 over x2 minus x1. I get negative 16 over 33. If you change that to a decimal, okay, it's negative 0.48, but you have to round to get a decimal. So I usually keep things as a fraction if they don't come out nicely, because you want them to, hold true as much as possible. Okay, let's put the pieces together. So y equals, we just found our slope, and if you use a decimal, that's fine. I'm not going to hate you. You're just not going to be as accurate. Plus the y-intercept of 38. Now, was the increase in the percentage of smokers constant, or did it vary? I'm going to read questions 2 and 3 together, and then we're going to come back. And does the model assume a constant decrease or a varying increase? Okay, I want to go back to the picture. So the model, or first of all, the data, the actual data is this line, right? This is the percentage of smokers. Would you call that constant or varying? Well, it's varying. It goes up and down. You never know where it's going to be. So the actual data is varying. Here's the model. The model is constant, and that's always, so the percentage of smokers varies, and the model is constant, and that's how it's always going to be. That's the purpose of using a model. Almost all data in real life varies to some degree. And it's hard to predict based off of this up and down fashion. But if you can say, okay, let's just call a constant model that approximates the data, that will allow us to predict. So that is the purpose of using a constant model. So, did we need the data here to create this model? And the answer is no, because we used this y-intercept and then we used these 2 points to find our slope. So no, we didn't use anything before that. If we would have, it would have changed our model. If the decrease had been constant from 78 to 2012, what would be the estimated percentage of people who had smoked at the turn of the century? Well, the turn of the century is 2000. So if 1978 has an x value of 0, then 2000 will have an x value of 22. So if we use our model, y equals slope times my x value, right? Because I'm using my x value of 22 for 2000 plus 38. Now, when you do this piece, negative 16 divided by 33 times 22, you get negative 10.67 plus 38. We would have expected 27.3% of Americans to smoke at the turn of the century. Okay, now let's compare this to the actual value. So 2000 is this value here. So the actual is 23 and the estimate was 27.3. And you can see that totally, if you look at this spot here, you can see that the model is the straight line, that the model is higher than the actual. So the actual, I spelled that wrong, is lower than the estimate. Or the estimate is higher than the actual. I don't care. Either way, you could say that. And then use the linear model to estimate the expected percentage of smokers in 2011. Well, remember in 2011, X has a value of 33. And because we used 2011 to create our slope, this is not going to, it's going to be exactly what they told us to. So these will cancel out. I get negative 16 plus 38. My y value is 22, which is what they gave us. Again, because that's the value that we used. We use the beginning and the end values to find our slope, and that's why it came out to be exact. So the whole purpose of using these linear models is to be able to predict values further out than what you just have right in front of you.